Observe a modern electric vehicle coming to a rapid halt. The wheel decelerates aggressively, yet the mechanical friction components remain completely disengaged. The vehicle stops without the brake pads ever touching the disc. This physical reality yields a distinct statistical anomaly in automotive maintenance. The brake pads on an electric vehicle routinely exhibit a lifespan of up to 60,000 kilometers. Halting a 2-ton mass at high speeds traditionally requires immense mechanical clamping force to bleed off forward momentum. Yet in this scenario, physical friction is entirely absent. If mechanical friction isn't stopping the mass, what invisible physical mechanism is absorbing all of that kinetic energy? This extended component longevity stems from algorithmic kinetic inversion, allowing software to handle the physics of deceleration that were once reserved for mechanical parts. This energy conversion flowchart illustrates traditional internal combustion engine deceleration. Kinetic energy is violently converted into waste heat through mechanical friction. Disposing of energy through thermal dissipation dictates unavoidable, continuous physical wear and tear on the brake pads and rotors. Electric vehicles bypass this mechanical degradation by utilizing a permanent magnet synchronous motor. To understand how this motor halts a vehicle without physical contact, we must look at its internal architecture. The electric powertrain transforms the problem of braking from a mechanical equation into an electromagnetic one. We will use a front-wheel drive architecture as the baseline model for this mechanical analysis. This profile vector diagram demonstrates dynamic weight transfer. When a heavy vehicle decelerates rapidly, its center of mass shifts forward, loading the front axle. By mounting the primary motor here, the hardware sits exactly where this kinetic load is concentrated. Before we analyze how the motor captures this massive load, we must establish how it operates under acceleration. The front-wheel drive layout serves as a geometrically optimal position for maximizing energy recovery. In Phase 1, propulsion, the high-voltage chassis battery acts as the singular source of direct current power. An onboard inverter translates this incoming DC power into alternating current. Inside this permanent magnet synchronous motor, the AC-powered stator creates a rotating magnetic field. This field physically drags the inner rotor's permanent magnets in a circle. This magnetic interaction drives the wheels, generating 150 kilowatts of power and 310 newton-meters of torque. During propulsion, electrical energy is strictly consumed to create forward momentum. Phase 2 begins the exact millisecond the driver lifts their foot off the accelerator pedal. The control algorithm instantly cuts all electrical power to the motor stator. At this microsecond, the 2-ton mass retains immense forward momentum. This kinetic energy forces the wheels, and therefore the now unpowered rotor, to keep spinning. This specific physical state is governed by a principle established in the 19th century, Faraday's law of induction. As illustrated in this diagram, the rotor's permanent magnets now sweep rapidly past the unpowered static copper coils of the stator, inducing a fresh alternating electrical current. The vehicle's sheer momentum backdrives the hardware. The motor is perfectly inverted into a generator. Inducing this new current triggers phase P, electromagnetic drag. The laws of thermodynamics dictate that generating electricity requires an equivalent output of mechanical work. In this vector diagram, we see that required work manifesting as physical resistance. A heavy negative torque pushes directly against the wheel's forward rotation. This resistance is the actual braking force. In Phase 4, onboard computers modulate this electromagnetic drag thousands of times per second to ensure a smooth, controlled deceleration profile. The newly harvested AC current flows backward into the inverter, where it is rectified back into direct current. Finally, this rectified current is deposited back into the high-voltage chassis battery, actively replenishing its 71.8 kilowatt-hour capacity. Regenerative braking is the capture of kinetic energy through applied electromagnetic resistance. Compare the two architectures during an identical high-speed stop. On the left, the internal combustion drivetrain relies on physical destruction via mechanical friction. On the right, the electric vehicle relies on magnetic resistance. The traditional system treats kinetic energy as a dangerous liability that must be destroyed to stop the vehicle safely. The electric system treats that exact same kinetic energy as a highly valuable asset to be harvested and stored. This process physically re-engineers deceleration from a destructive mechanism into a productive one. This mechanical efficiency translates directly into empirical maintenance data for consumers. Comparing 5-year maintenance expenditures, a standard internal combustion vehicle incurs between 20 and 30 million rupiah, largely driven by friction component replacement. For an equivalent electric vehicle, that cost drops to between 8 and 12 million rupiah, a reduction directly attributable to bypassing physical friction. Physical brake pads are now only engaged in the final moments of a complete stop or during aggressive emergencies, safely preserving their lifespan up to 60,000 kilometers. This algorithmic braking alters the total cost of ownership matrix for both fleet operators and private owners. The permanent magnet synchronous motor serves as a closed-loop energy management system, integrating propulsion and recovery